Hello and welcome to my second video on registers. This one is going to be on a serial adder with control circuitry. And on your screen here is showing the completed circuit. For this one, we're not going to have any design steps or anything because this was derived from what the teacher gave us. But I can show you how it works, kind of its functionality, and then the meta, the higher tier abstraction that we use in order to make things like this. So first I will show it working. It's going to perform the operation C plus 7, that's in hexadecimal. So we can go ahead and load that up. So we'll have C plus 7, and you load that into these two registers here. And then let's see, I got to I need to auto tick. Okay. And then we'll click start, and then we'll turn start off, and it's working its magic, and then it returns the value 1-3 in hexadecimal, which I believe is the answer to that. I haven't read hexadecimal in a while, so I'll just kind of let's see here. Okay, perfect. Yep, so it's supposed to be 13. I just did that on calculator just to double check. And get back to my spot here. Okay, perfect. So that's it working its magic. And now we can go ahead and identify the 7 parts of the data path. And that's that higher level abstraction that I was talking about earlier. So I can actually, let's see here. So it's broken down into these 7 different components. And I'll just actually flash this on the screen real quick just to show you guys. Let's see. So we have these two these two boxes, control and data path, and then we have 5 arrows, which basically represent signals, or like information moving from one component to another, is kind of how I like to see it. So if you take that model, then we can start with the external signals. In this entire circuit, we only have one external signal, and that's whether or not we're starting or stopping, and that's obviously the switch right here. And let's see, so for the control area, it's just given by this control logic here. This basically makes the decisions for everything. It's saying, okay, well, are we going to load the bits onto the register? Are we going to actually do the sum? Or are we going to go back to idle mode? One of those 3 options. And then we have the control signals. The control signals are, so you could say it's this wire here that's basically telling this mux what to do. You could also say it's the max 1 and max 2, or this reset CT tunnel, which tells you to reset the counter. And these max 2 and max 1 tunnels have their own functions in regards to, they're basically the things that make the decisions. What state are we going to switch to and from? Let's see here, and then the status signals are Q1 and Q0. They're held in the state memory, and it's just saying, okay, this is currently what state we're in. We're either in idle mode, or we're in adding mode, or we're in loading mode. And so that's given by these JK flip-flops here, which are, as you can see, determined by max 1 and max 2. So it's a sequential circuit. So input data are these 2 registers right here. It's given by this data path. So we have 2 values, and then we input them into this right here is basically a function. We input them into our function, and then we get an output, which is our this register here, which is also coincidentally the output data, and that's stored in the sum. So, yeah, that is the data path control model one-to-one comparison there. And then the last question is discuss why it's useful to design circuits with control units. And I feel like this is a much more common sense question. However, people might be tempted to make it more complicated than it really needs to be. We use control units so that we don't personally have to do their job. I mean, that's the whole point of automating these things. If we didn't have this control logic here, I would have to manually tell the machine when to load. I would have to control the clock, or maybe even if you had an auto-enabled clock, like you would have to tell it when to load, when to add, when to go idle, and basically it just does it for you. And that's that's effectively self-explanatory. It's why do you want something to do something for you so that you don't have to do it. It makes things more complicated. Obviously, this is a the original circuit was just this serial adder right here, and that's it. And by adding this control logic, we now have this literally motherboard-looking thing. So it definitely makes it more complicated in the short term, but in the long term, well, now you don't have to do anything other than hit start and then put in your two input values. It's effectively a function. I love how on the slide it says, see at the bottom here it says, and that's how you add 9 plus 4. After showing us how to build this whole thing, and that's how you add 9 plus 4. And in reality, it's adding 9 plus 4, but it's having a computer add 9 plus 4 for you. And there's a very big importance in understanding the value of that and how that differs from simply adding 9 plus 4. So, all right, that's pretty much it for this video. I don't really have any more questions to cover here, so thank you for watching, and we'll see you in the next one.